Welcome back to the channel. Today we're going to discuss about electric potential energy. But before directly landing on to potential energy, we have to discuss about the potential due to some complex system. Because in our last video we have discussed on two simple cases. So first we're going to obtain the potential of those complex cases, then we're going to calculate the potential energy. So first we will be studying about potential due to electric dipole at any arbitrary point. As you can see, here we have placed point P and the dipole has been placed. Now here the point P has been placed at any arbitrary position. That is, it is neither on the axis nor on the equatorial plane. So we have marked the point P with respect to charge Q1 and Q2 placed at distance R1 and R2. And right from the midpoint of the dipole, it is placed at a distance R, making angle theta. So let's see how we proceed over to obtain potential at point P. So the potential at point P will be the sum of the potential due to charge plus Q and charge minus Q. And as you can see, 1 by 4 pi epsilon naught Q by R1 for the positive charge and Q by R2 for the negative charge. Now we have to replace R1 and R2 in terms of R, and to do so we are using vector additional formula. So in vector addition formula we use here obtain the vector sum of A vector and R1 vector, and thus the resultant will be R vector, and hence we obtain R equals to R1 plus A, and hence we obtain R1 vector is equals to R minus A. Now from here we require to obtain the magnitude of R1. How we do so? Just see, the magnitude of R1 vector will be in this form. Will be R square plus A square minus 2AR cos theta, and thus from squaring it over we obtain R1 square, and similarly we can obtain R2 square also, because R2 square will be obtained from the equation that will be R2 vector equals to A vector plus R vector. Now if we move forward, we come up with a consideration that R must be very greater than A vector. As you can see, R is considered very greater than A. So what we have to do? Taking R square constant, and we obtain this form of equation. So here we obtain a term that is A square by R square. So this will be negligible and considered to be 0. How negligible? Because R square is greater than A, and hence A by R will be small. So A by R square will be further negligible and small. So it is neglected, and thus we come up with the approximation where R1 square can be written as this type of equation. Similarly, R2 can also be written with this type of equation. But we require to focus. To obtain the potential, we require the value of 1 by R1 and 1 by R2. 1 by. And here we have obtained direct value of R1 and R2. Hence, by obtaining the inverse of R1 and R2 and using binomial expansion, we obtain this kind of equation. If you focus over the fact, it has been written just in similar form, just putting the value of R1 in 1 by R1, and we obtain as such. The power has been shifted over to minus, and the half appears due to the square root of that R square value. Now when we put binomial expansion, applying the formula, we include the value as such, 1 by R into 1 minus 2a cos theta divided by r into minus of half, and rest terms are neglected. So it has been written as 0, and thus 2 get cancels and this minus cancels up with plus. Hence we obtain this kind of form. And similarly for 1 by r2 we obtain this kind of form. And hence we further proceed to place the value in 1 by r1 and 1 by r2 to obtain this kind of equation. If you perform the calculation, you will find that v equals to will be q into 2a cos theta by r square and 4 pi epsilon naught, where q into 2a can be replaced as p, that is the value of dipole moment, and it depends on the angle theta with cos function. So with this we can conclude with two type of cases where theta will be 0 or 180 degree and theta will be 90 degree. Theta 0 or 180 degree stands as if the minus q and plus q charge has been placed and the point P lies at this point or at this point. This will be for 0 degree, this will be for 180 degree. For both of these cases, we will obtain the value as 1 by 4 pi epsilon naught p by r square, and plus or minus sign appears with the value of cos function. And for the case 0 equals to 90 degree, where the point P is placed at the equatorial plane, and hence we obtain the potential as 0, as we have already proved this in our earlier video, that potential at equatorial plane must be 0, and hence we obtain such from the general formula. Next, after discussing about dipole for a generalized case, now we're gonna discuss about potential due to a system of charges. That will be, as you can see, a point P has been placed, and with respect to that point P, a system of 5 charges has been placed, that is Q1, Q2, Q3, Q4, Q5, placed at a distance R1, R2, R3, R4, R5. So now this is a complex system, more complex than the dipole. So for which we require to obtain the potential at point P in space. So it is a very simple procedure. Just we require to obtain potential for a single charge separately. Like for potential for Q1 is obtained as 1 by 4 pi epsilon naught Q1 divided by R1, that is the distance between point P and the charge Q. Similarly, we gonna obtain the potential due to charge Q2, Q3, and further we gonna proceed for all the charges. And thus, therefore, to obtain the total potential at point P, we just require to sum up all the potentials separately for all the charges, and that is we obtain a generalized formula as the sum of all the potentials for the various point charges placed in space. So adding up, we're gonna get the total potential at point P. So next, we will be studying about potential due to a charge conducting sphere. As we have already studied that for a charge conducting sphere, to obtain the electric field at point P, and the generalized formula is 1 by 4 pi epsilon naught q by r square. It's just a simple formula. And as we know, this electric field only present till the outer surface of the sphere, after which no electric field is present. So just with the help of simple formula, we can obtain the potential at point, that is V equals to integration of E dr. And similarly, we followed the steps like earlier, where the integrational limits are from infinity to r. This comes directly from the definition of potential, that was to bring any body from infinity to point P, which is r distance away from the center, and just simply follow that calculation, we obtain this kind of equation for the potential at point P, where point P is arbitrary point in the electric field. Now, if we try to plot the variation of potential at point P, placing point P at various locations, we're gonna obtain this kind of graph. Now, how it is obtained? Let's see. If we stand on the surface of the conducting sphere, right on the surface of the conducting sphere, we're gonna get a constant value that will be 1 by 4 pi epsilon naught q by r, where r stands the radius of the conducting sphere. Where r stands the radius, let's find. So at this position, small r will be equals to capital R, that is the radius of the conducting sphere. This will be radius of the conducting sphere. Now, if we further proceed, move away from the charge conductor, we will see that with the variation of 1 by r, 1 divided by r, the potential decreases. And hence in the graph also the variation has been shown that with 1 by r function, the potential decreases as r increases. But we know that electric field in this location will be 0 inside the charge conducting sphere. Hence, potential must be some constant, because if potential is constant, differentiating it, we will be obtaining electric field, and that is 0. Hence, if we integrate the 0 value of electric field with respect to dr, we gonna obtain some constant value, and that is V0, and due to which the potential remains constant for the distance and for the total distance that lies inside the charge conducting sphere. It is V0. So in this way, we get to study about the potential due to a simple conducting spherical shell. So finally, now we are going to discuss about potential energy. So earlier we have completed everything about the various potential we can obtain from different cases. Now finally we are landing up to potential energy. So let's see. What is potential energy? The work done to assemble a system of charges by bringing them from infinity is known as electrostatic potential energy. Now let's see. Now in this space, two charges Q1 and Q2, which are lying far away from each other. So let's first bring Q1 from infinity to a point in our nearby space. So Q1 is present. So due to the presence of Q1, a field will be generated all around Q1. And next, we bring that point charge Q2 near Q1. So as Q2 appears within the field of Q1, as you can see, this dotted line has been shown just to show that now it is within its field and it is experiencing the potential due to Q1, and hence we're gonna experience this kind of potential due to the charge Q1, that will be 1 by 4 pi epsilon naught Q1 by R1, the distance between charge 1 and charge 2. Hence, the work done was 1 by 4 pi epsilon naught Q1 Q2 by R12. As we have already done how to obtain the work done or the potential energy. So, this is the potential energy due to Q2, the most simplest case that we can perform. First and foremost, we have already mentioned one thing, that to bring from infinity. Why to bring from infinity? The total experiment, not the experiment, the total thought process was done in such a way that in an open space when no one is present, suddenly we bring the charge Q1, which is not going to experience any kind of force. Just Q1 alone will be standing. So when Q2 appears, it is going to experience only the force due to Q1. Other than that, no force is present or no field is present. So thus we obtain the potential energy gained by Q2 due to the presence of Q1. Now this is the most simple case of potential energy. So let's make it little complex. by introduction of a third charge Q3. So now when Q3 appears, it is going to experience the field due to Q1 and also the field due to Q2. And hence the total potential energy of the system will be, as you can see, the total energy where Q1 and Q3 potential, due to the presence of Q1 and Q3 we measure the potential energy, due to the presence of Q2 and Q3 we measure the potential energy, and also due to the presence of Q1 and Q2. Hence the total potential energy becomes the all the combination of potential energy possible within the system and sum of all the combinations, and hence we obtain the potential energy of a three charge system. It can also be obtained for n number of charge system. It is going to be much more complex, and if n becomes larger, so we have to write down all the possible combinations of potential energy that will be possible among all those charges. Now there's a question arising, so you have to find out the value of the energy in electron volt. As we are studying electrostatic potential energy, later on we will have to face this kind of unit that will be in electron volt. Let's try to measure the value. Now we are going to discuss about potential energy on charges in presence of an uniform external electric field. Let us consider just a uniform external electric field is present, whatever be the source of the field. We just simply bring a charge, let's say just bring a charge Q within that field Q1. Hence what will be its potential energy? Its potential energy will be obviously VR, that is the potential it's going to experience into Q1. This is gonna be its potential energy. Now let us consider another charge Q2 appears within the field. Now what will be its potential energy? Obviously we will have Q2 VR into Q2. But when Q2 appears, this is not only the potential energy. Some other potential energy is also present. Hence the total potential energy U will be addition of Q1 plus Q2 plus there will be potential due to Q1 Q2 by R12 by epsilon naught. So hence we obtain the total potential energy for this system. Hence we obtain the total potential energy of this kind of system when we bring charge Q1 within the field and later on we bring another charge Q2 within the field. So on, if we continuously start increasing the number of charges Q3 or Q4, whatever it is, so we have to continuously add on this kind of potential energy equations along with this combinational form to obtain total potential energy whenever a charge is brought within any kind of external electric field. So here we are going to discuss about potential energy of a dipole in presence of uniform electric field. We have already seen this kind of case when we have studied about dipole and the torque generated on dipole when present in a uniform electric field. Now this kind of case will be observed here. The torque will be generated, but due to the generation of a torque, the dipole rotates, and which the dipole rotates in the possible directions that has been marked with this arrow, and due to the rotation of this dipole, some potential energy is gained by the dipole. So let's see. The torque that is generated by the dipole stands as tau equals to P cross E, which we have already started. So without further going into those details, let's find what will be its work done. Let us see the dipole rotates, and due to its rotation, now its angle change from theta 0 to theta 1. Initially, it was at an angle theta 0. So the initial angle was theta 0. Now the final angle, it changes to theta 1. But we should always keep in mind while placing its values, because we have to keep in mind in which quadrant the angle is measured. Now let's see how the work done is obtained. So work done for rotating the dipole stand as W equals to, just we have to directly integrate for the angular displacement, and so torque into angular displacement, and integrating over from theta 0 to theta 1, from theta 0 its initial point to theta 1, we integrate torque into angular displacement. So directly placing into the value Pe sin theta d theta, and we obtain finally the work done as Pe cos theta minus Pe cos theta minus 1. So which is the value of the work done in rotating from theta 0 to theta 1. Now let us consider a special case, that is, we consider the initial field or the initial angle as 90 degree and the final angle theta 1 as theta. There will be something special about this theta 0 case for 90 degree. So when we obtain the potential energy or the work done by the dipole, it stands out as Pe cos pi by 2 minus cos theta. Cos pi by 2, as you know, stands to be 0, and hence we obtain the result as minus Pe cos theta, or P vector dot E vector with a minus sign. So why have we considered for theta 0 equals to 90 degree? At this position, for theta 0 equals to 90 degree, that is, the dipole will be standing perpendicular to the field. Now at this position, the dipole is not going to experience any kind of energy, or that will be the zero potential energy position. So the work done from that zero potential energy position to whichever or any point in the electric field due to its angular displacement is the potential energy gained by the dipole. So hence I can say that with the final expression of U equals to minus P dot E, we obtain the potential energy in presence of uniform electric field for the dipole. As you can see, the definition appears down below the screen. Now we are going to discuss about the various positions of the dipole along the field, with which we are going to measure the most stable and the most unstable position of the dipole. Now as you can see, now the dipole is lying along the axis of the field, and hence we obtain the most stable equilibrium condition for theta equals to 0. So we obtain the potential energy, the minimum potential energy, as minus Pe. Now if we further rotate the dipole by 90 degree, we obtain a zero potential energy condition. Just we have mentioned before, the zero potential energy condition. Now if we further rotate the dipole, which will be completely opposite to the direction of the field, and we obtain the most unstable equilibrium condition. In the unstable equilibrium condition, and we obtain the potential energy as Pe. So it is the highest obtainable potential energy by the dipole. So here we are discussed about the variation of the potential energy within this graph. So at 0 we obtain the minimum potential energy, that is minus Pe. At 90 degree we obtain the zero potential energy. At the highest point, that is the most unstable equilibrium condition, we obtain the highest potential energy Pe. So if we continuously go on rotating the dipole, so we gonna get a continuous graph, and it should be in this nature. It will be mostly in sinusoidal nature because the presence of the cost function in the potential energy expression. So here we end with the topic of potential energy